This is Simple Machines Practice for Physics with Technology. So we'll be trying to apply the equations we've now learned about simple machines. The input versus output work equation, mechanical advantage, and efficiency. Mary, a 460 Newton actress, playing Peter Pan, is hoisted above the stage in order to fly by a stagehand pulling with a force of 60 newtons on a rope wrapped around a pulley system. What is the actual mechanical advantage of the pulley system? So we know that mechanical advantage is either output force divided by input force, or input distance divided by output distance. In this case, we only know about forces, so the input and output distance version of mechanical advantage won't work for us. So when you lift something, you have to lift up with a force equal to the weight of the object. And just by virtue of the units, 460 Newton Mary, her weight is 460 newtons. The input force is the force you exert when you're using the machine. So the stagehand is pulling on the rope with 60 newtons. So the input force is equal to 60 newtons. So we can calculate our mechanical advantage. Output force, 460 newtons, divided by input force, 60 newtons. And I will need my calculator for this. 460 divided by 60 gives us 7.666, so let's call it 7.7. Mechanical advantage is not always a whole number. Sometimes it's decimals, and that's just fine. There are no units for mechanical advantage. It's just the rating for how the input and output forces are related for a simple machine. Next example. Winnie, a waitress, holds a 5 Newton tray stacked with 12 3.5 Newton dishes in one hand. So this is information about what she's lifting. The length of her arm from her hand to her elbow is 30 centimeters, and her biceps exert a force 5 centimeters from her elbow, which acts as a fulcrum. How much force must her biceps exert to hold the tray? So this is a case of a class 3 or a type 3 lever. Rather than considering the sort of anatomical drawing here, I'm going to reduce this to an actual lever-looking thing, right? So a stick with the fulcrum, or the pivot point, at the end of the stick. This is the elbow joint here. This is the pivot point. The problem tells us that the biceps muscle connects 5 centimeters from that pivot, from that fulcrum. And the biceps is the input force. So the biceps exert an input force here, 5 centimeters from the axis or from the pivot point or the fulcrum. And then her hand is the output force. And her hand, it says, is 30 centimeters from her elbow. So we know the distance from the pivot, the fulcrum, to her output force. And the output force needs to be the weight of all the stuff she's holding. So she holds a 5 Newton tray plus 12 3.5 Newton dishes. By order of operations, I need to do 12 times 3.5 and then add 5. So 47 newtons. She's lifting 47 newtons of weight. That's the output force. That force is exerted 30 centimeters from the fulcrum. Her input force, the force her biceps muscle exerts, is exerted 5 centimeters from the fulcrum, but we don't know that force. That's what we want to know. So I've got distances and one force. This suggests using the input work equals output work equation. This is sort of the foundation of simple machines. So force times distance in equals force times distance out. All right, so on the input side, I have the unknown biceps force. On the input side, I have a distance from biceps connection to the bone to the elbow joint of 5 centimeters. On the output side, I have a force of the weight of the tray and the dishes, 47 newtons. And I have a distance from the place where that weight has to be sustained to the fulcrum of 30 centimeters. So I check. If you don't like the way the units look, you can rewrite it without units. Force times 5 equals 47 times 30. 1,410. So to finally solve the problem, I have to divide both sides by 5. And I find that the force is equal to 282 newtons. So in a class 3 or type 3 lever, you're going to find that the input force has to be rather larger than the output force. It sort of does the reverse of a usual simple machine. But it's very much in play in our skeletal systems. So the last example is the Ramseys. The Ramseys are moving to a new town, so they've called in the Acme Moving Company to take care of their furniture. Debbie, one of the movers, slides the Ramseys' 2,200 Newton china cabinet up a 6-meter long ramp to the moving van, which is 1 meter off the ground. Okay, so before I do anything, I'm going to try to figure that out, right? Here's my ramp, and it's 6 meters long, and it lifts something up to the back of the moving van 1 meter above the ground. So that tells me the dimensions of my ramp. And then I know that without the ramp, she would have to lift 2,200 newtons of china cabinet straight up. And that 2,200 newtons is the weight of the china cabinet, not explicitly stated, but I'm inferring it from the unit of newtons. Okay, so A, that looks like a D. A is, what's the mechanical advantage of the incline? Well, I know one of the forces, but I don't know how much force she pushes up the incline. So I can't use force, but I know the length and height of the ramp. So I'm going to use the distance version of mechanical advantage. So mechanical advantage can be found by input distance divided by output distance. The input distance is the length of the ramp. The output distance is the height of the ramp. So my mechanical advantage is 6. Part B. If Debbie must exert 500 newtons to move the china cabinet up the ramp, so now we know what's happening on the ramp. She's pushing with 500 newtons rather than lifting straight up with 2,200 newtons. What's the actual mechanical advantage of the ramp? So this time I'm not going to use distances. That's the geometry of the ramp. That's the ideal version of mechanical advantage. Now I'm going to use force. So the actual force she had to exert compared to the force she would need to exert to lift the china cabinet straight up. So she actually applied 500 newtons. The china cabinet weighs 2,200 newtons. And again, now I need my calculator. Which, let's see if I put it over here. Sure. You can kind of see the screen. 500. Wait a minute. I just flip-flopped those. Wait a minute. Output is lifting 2,200. Input is how much she pushes along the ramp. I flip-flopped those forces. I hope you caught that before I did. Output force is what it would take without the ramp. Input force is how much force she exerts using the ramp. So our actual mechanical advantage is 4.4. We don't get in real life, in real use of this ramp, a mechanical advantage of 6. 6 is ideal. If there was no friction, we would have a mechanical advantage of 6. In real life, we get a mechanical advantage of 4.4. Our final question then is, what's the efficiency? So efficiency is useful work out versus total work in. So the useful work we get out is to lift 2,200 newtons, 1 meter. I could calculate that. And then the total work we put in is pushing 500 newtons for 6 meters. I could calculate work out and work in and find efficiency. But I could also remember that efficiency is actual mechanical advantage divided by theoretical or ideal mechanical advantage. All of these are multiplied by 100% to make it a percentage instead of a decimal. Excuse me. Since I've already just calculated mechanical advantages, I'm going to take the shortcut. So my actual is 4.4, my ideal is 6. I end up with 73.3%. So this machine is 73.3% efficient, not 100%, mostly due to friction. You are now going to work with your friends and neighbors on the remaining worksheet, which deals with pulleys. You have single fixed, single movable, block and tackle of one of each. Then you have a block and tackle system with 3 pulleys top and bottom. I would suggest thinking about number of support strings. And then you have a question about conservation of energy. I'll leave my solutions with the substitute teacher, and you can check your answers once you've tried it, but you must try it on your own first. Good luck, and I'll see you on Tuesday.